In this video, we're going to go through a worked example of using bond enthalpy to find the enthalpy of a reaction. Now, I've left out the states of matter in this one for now, but they would normally be given. So here I've got the combustion of methane gas. So it's the complete combustion making water molecules and carbon dioxide. In this we would be given a whole range of bond enthalpies. They may even give carbon-oxygen single bonds just to check that we understand what sort of bonds are actually in our molecules, in our substances. So what I normally do is I start by quickly sketching those, and you'll notice that when I've got more than one of something, I draw that many of them. Now that works if the number is 2 or 3 or 4, but when you get up to large numbers, a bit of maths might save you a bit of drawing. So I've drawn my methane, I've drawn my oxygen, and I've drawn 2 of them because that's our mole ratio. I've drawn my 2 water molecules, and I've drawn my 1 CO2 molecule. The reason I'm doing that is to look at all of the bonds that need to be broken, and all of the bonds that need to be made. Now, bond making is exothermic, so this is why we're going to subtract their bond enthalpies from this to make these exothermic or negative values. And bond breaking is endothermic, so it requires energy to break these chemical bonds. So that's sort of like your activation energy, as it were. So the way I do it, so that I don't make a calculation mistake, or if I do, I still get some recognition for my work in my answer, is I draw my equation out, so splitting my page in half down the middle. So I'm going to work out the enthalpy for all of the bonds broken, and separately I'm going to find the enthalpy of all of the bonds made. Again, using that information that I would be given. So I've got 4 CH bonds being broken. So I'm going to break all 4 of them. And that will require 4 times 414 kilojoules per mole. I've also got 2 moles of oxygen, so I need to break the oxygen-oxygen double bond twice. They're 498 each, so I'll double that. That gives me a total activation energy, if you were, of 2,652 kilojoules per mole. Then separately I'm going to do the number of moles, the enthalpy, bond enthalpies for the bonds that are being made. And I'm going to do those separately. So I've got 2 water molecules, each with 2 OH bonds. So 4, 2 times 2, of the OH bonds. So 4 times 465. I've also got CO double bonds because that's carbon dioxide structure. I've got 1 of those, so 2 CO bonds in there, so 2 times 800. I add these up and I get 3,460 kilojoules per mole. In an answer, in an exam, I'm going to make sure I do actually include both of those values. Just in case I've made a silly mistake somewhere, I can still get some credit for either working out the broken or the made correctly. Then I do this simple subtraction and I get negative 808 kilojoules per mole. Now you'll notice I didn't put the kilojoules per mole in here when I was just working with numbers. It would be good to, but you don't have to. But I need to make sure I've got that unit in my final answer. If I don't have that unit in my final answer, then it's wrong. Kilojoules per mole is the unit for the enthalpy change of a reaction, so it needs to be used in the final answer to make it meaningful.